We now want to talk about the issue of centripetal acceleration. And centripetal acceleration occurs when an object is moving around a curved path as opposed to a straight line. Now, the archetype of this motion is the perfect circle. So imagine an object constricted to a circle, and let's say that its speed is also constant. Now, if the speed is constant, that means the magnitude of the velocity is constant. But here's the rub. Remember that velocity is a vector, and vectors include both direction and magnitude. So as my object is moving around this circle of radius r, and we'll call this initial radius here r1, and we'll call this the initial position, and as the object is moving around the circle sometime later, this should be r2, not r squared, sorry. We'll call that position r2. And so they're moving with an initial velocity v1, and then after some time, their velocity vector has changed direction, and so they have a new velocity v2. Now, you can change speeds as you're moving around. The analysis does not change, but it's simpler to consider the case where we have constant velocity at first, or a constant speed at first, rather. Right, but the issue is because the direction is changing, because vectors have magnitude and direction, because the direction is changing, therefore the velocity is changing. And anytime you have a change in velocity, you have an acceleration. And that's what we want to find. Now, if I make an angle here, theta, okay, remember that the velocity vector of an object moving around a curved path will always be perpendicular to the path. So in other words, as my object is moving around my circle here, right at this instant, the velocity vector is pointing straight up. So if it were to stop being constricted by the circular motion, once it reaches this point, it would just continue to move in a straight line. You can convince yourself that this is the case because let's say I have a sling and I'm slinging a rock around my head. If I want to project the rock straight forward, I have to let it go right when it's at my side, So if I'm swinging my rock above my head and I want to shoot it forward, then as the swing or the sling is right here, the velocity vector of the rock is straight forward, and that will cause the rock to move directly ahead of me. So a few instances later, the new velocity vector is pointing in this direction. But these are always going to be right angles, okay? These are always going to be right angles. So what we can do, remember that vectors we can move around. We can move them around with impunity. So if I look at my initial triangle here, and I just transpose it over to here, right? What we have is a triangle with my three sides, R1, R2, and the displacement vector between the two is called delta r. And if I take my v2 and move it down here, as over here, then I have this triangle as well, but because these are always going to be perpendicular to each other, however my r vector changes is also going to be the same rate at which my velocity vector changes. So what we have here are called similar triangles. Now, similar triangles are also going to be isosceles triangles because the radius of my circle is not changing, and if I'm moving at a constant speed, then the magnitude of these arrows is not going to be changing either. So these are going to be similar isosceles triangles. And what we can do with that is there's a property that says if I take the short side of a triangle and divide it by one of my isosceles sides, well, it doesn't have to be the short side. It can be one of the non-isosceles legs divided by one of the isosceles legs. For any two similar triangles, that ratio is going to hold constant. So I can take delta V over V and delta R over R, and that ratio will stay constant because these similar triangles are similar. Now, what we want to do, remember, is that acceleration is delta V over delta T. Right. Acceleration is delta V over delta T. So the goal here is to get this in the form of delta v over delta t, and this will give us the acceleration of an object moving around a circle. So what I can do is multiply both sides by v, and that'll give me delta v is equal to v times delta r over r. And then I just divide both sides by delta t. And now look at this term right here, delta r over delta t. That is displacement over time. So that's the same thing as velocity. And if my angles are short enough, in other words, if my time spans are small enough, okay, then my delta r here is going to approach the distance along the circle that the object moves. So if delta r over delta t approaches the distance along the triangle that the object moves, that is just the magnitude of the velocity. So delta r over delta t, when t is small enough, goes to v squared. And so the acceleration due to moving around a circle, so we call this centripetal acceleration, I'll call it a sub c. A sub c is equal to my change in velocity over my change in time, but what that boils down to mathematically is just for an object moving at constant speed, the magnitude of the speed divided by the radius. Okay, now you might be tempted to think, well, velocity is a vector, so why isn't this side a vector? Well, it technically is a vector, okay? Yes, velocity is a vector, and so is position, all right? But we're writing it kind of in a scalar form because really at the end of the day, we're more concerned about the magnitude of the centripetal acceleration than the direction. What is the direction, however? Let's look at this. The direction of the centripetal acceleration will always be directed toward the center, okay? The direction of my acceleration will always be directed toward the center. If it were not, okay, if the direction were not toward the center, then it would be pushing the object outward as opposed to trying to pull it inward. What's happening is because this object right here has this velocity vector in this direction, it wants to keep moving in this direction, but the acceleration pulling it toward the center pulls the velocity vector around, and so then that's what causes it to move in the circle. So the direction of this is going to be always toward the center of curvature, and the magnitude is written as this. All right, hope that helps, and we'll see you next time.